charge of research, applying these technologies to help develop, improve performance, health, and well-being. One of the areas we've been focused on recently is using the insights from neuroscience to rethink the processes of learning and gaining expertise. Now, we know that the traditional tools that educators and coaches and instructors use to evaluate performance are pretty good at telling us how we perform. We've all taken plenty of tests. But what our technologies do is open the window on the brain and give us information on why we perform the way we do. So one of the things that we've been doing is mapping the brains of experts across a wide range of disciplines. We've had access to mapping the brains of Olympic archers, expert marksmen, scientists and engineers, PGA golf pros, and a variety of leaders, both civilian and military. And the goal then is to use that expert brain map as a training goal for novices to achieve to help move their brains closer to that of an expert. So what happens in the brain when we learn? The cells of the brain, the neurons, are constantly communicating via millions of chemical and electrical signals. When a novice begins learning a new task, many regions of the brain light up and work together to achieve that construction of the new neural pathway for learning that task. As you practice the task, the neural pathway becomes strengthened by eliminating or pruning all of the irrelevant connections and then streamlining and strengthening that pathway so that when you master a skill, it can be automatically executed. This is the scientific basis for Erikson's theory that was highlighted in Malcolm Gladwell's book Outliers, that it takes 10,000 hours to practice to master a new skill. That repetition supports, strengthens, and streamlines that neural pathway. However, our real-world research suggests that the 10,000 hours to expertise theory may be a myth. We found that by training novices to first recognize their own mental state and then help shape their mental state towards that of an expert, we could greatly reduce the overall time required to train and gain mastery of a new technique. So the way that we did this was, first, we wanted the trainees to be in the optimal state for learning. And one of the things we recognized very early in our research was that high anxiety levels were inhibitory to new learning. So when our sensors sensed high anxiety levels, we trained the trainees to control their breathing and heart rate and reduce their anxiety levels. Then we developed software that provided feedback training where we compared the novice's brain to that of the expert, and using a variety of visual, auditory, and tactile feedback cues, helped them shape their brain towards that of an expert. This is an example of an archer who's receiving tactile feedback through a small buzzer on his collar that's telling him how and when he's achieved the expert brain state. And we were able to move him from the intermediate state to the expert state. Now, in our study of 300 individuals, we found that 85% of people could achieve control over their brain state and move towards the expert state even after just 1 day of training with this feedback. And we saw a 2.3 times acceleration of marksmanship skill training in those first trained to achieve the expert brain state. In addition, we found that by training novices to control their mental state, that they could move in and out of this state when it was desirable. And we found now that this training approach may be applicable across a number of different skills and exercises. So the implications for learning and how we learn are profound. one thing that we all agreed as we were working with coaches and educators, both military and civilian, is that the traditional approach to classroom training is largely ineffective for many people because students learn at different rates and they learn differently from different instructors and presentation styles. Now, using these neuroscience tools, we can actually objectively assess how students are learning in different environments. And one area of particular interest is how do social interactions facilitate learning? And one of the studies that we've done is with high school students collaboratively solving science problems, where we were able to identify by monitoring their brains very early in the process whether they were going to reach a successful conclusion in the problem-solving session. We have also been working with graduate students and college students to assess what happens in social interactions when you're learning to solve very complex problems and approach new tasks with new critical thinking and creative thinking. This is an example of a group of MBA students collaboratively solving an ethical decision task. And what we were able to do is by monitoring their brain states, we could establish how peer-to-peer interactions often lead to accelerated learning of complex skills and problem solving when compared with the traditional classroom environment. We also showed in this study that we can identify, by mapping the brain states of the team, the emergence of leaders and how those leaders influence the group process. So the implications across the board are profound. We envision a future where these technologies can be used to accelerate evolution by helping us to further understand ourselves and each other. Thank you.